Welcome back to my classes on fundamentals of electrical engineering. We are now going on to Fourier series. In fact, two of these sessions were recorded earlier, but I couldn't post them since due to some particular personal problems. So this time I am back to signals and systems. That's the fourth module, and we are doing the Fourier series. Okay, Fourier series. Just the name Fourier seems to evoke certain problems, but I'd like to say that it's actually a step ahead of Laplace transform in the sense that more information is condensed, especially because the frequency is essentially essentially the backbone of the Fourier transforms as also for Fourier series. And in such a context, when frequency is involved, there are methods by which multiplication can be converted to additions, and powers can be converted into multiplication. So a lot of data crunching is possible. That's the reason why Fourier series as also Fourier transforms are so widely applicable even now in several contexts. You come to Fourier series, the goodness of it all happens to be that a periodic signal, of course, only a periodic signal can have an alternate representation. Okay, it's just a representation using a few coefficients. Okay, and these coefficients are not as so many, or in other words, these are the convergence points. So there are, of course, there are numerous numbers. Because you allow n to go from minus infinity to plus infinity, or from 0 to infinity, based on either you use the trigonometric representation or the exponential representation. So that's all that's there. But so in general, there are only three coefficients when you look at the trigonometric representation. On the other hand, you have only one coefficient when you are looking at the exponential coefficient. I always prefer to use the exponential version here, but then for certain types of periodic signals which have some kind of symmetry, it's useful. The other one is more useful. Okay, so here we will have a brief glance at some of the aspects associated with the symmetry. Okay, if there is no symmetry, of course you have the general representation in the trigonometric representation, which I'm not going to relate now, as also in the exponential version, which are all given in this first slide. Okay? But on the other hand, if you're having even symmetry, then then for in the trigonometric version, the sign quantities disappear. That is, the coefficients associated with the sign quantities disappear. On the other hand, for even symmetry, for the odd symmetry, both the DC value, which is signified by A0 by 2, as also the cosine coefficients, which are cosine components which have coefficients as signified by AK here, disappear. So that's an ease of doing the problem when you are having Fourier series representation again. And then you go further if you have what is called as half-wave symmetry. Even and odd are very easy to understand. For even symmetry, the waveform is spread across, equally along both the axis of t equal to 0. Okay, because we are looking at time domain functions essentially when we are talking about signals and systems here, and when we go on to control systems as well. But when you look at we have a look at odd symmetry, it means that the periodic wave or waveform is such that you have to such that it if you fold it over t equal to 0, then again one more fold that is along the magnitude axis will give you the same picture. So this is the understanding of odd symmetry. Okay, but there's another symmetry which is of more use, which is the half-wave symmetry, wherein you can shift the signal by half the period. Okay, so period is very important. Okay, so period is just telling us where the repeatability is going to set in again. So once you shift the entire waveform by half the period, then if you reverse it or if you reflect it, then you get the same signal. Okay, so that is identical. In that case, there's a little more to be said, in the sense that it can have both odd and half-wave symmetry, or it can have even and half-wave symmetry. If one of them is the case, it depends upon what was mentioned earlier. Additionally, the even the coefficients associated with even k, okay, will disappear. Okay, so let's go for some of the problems. Okay, the first problem is very easy. A periodic signal is given. Okay, so let's look at periodic signal, which is having three components. Okay, of course, the three terms. Okay, rather than three components, I would say that there are three terms, and each of them have different magnitudes. Okay, the magnitudes are 30, 10, and 6. Okay, they are all no, they are all not all sinusoidal. Doesn't matter. Are not all sinusoidal. One is cosine, or they are all sinusoids. So that's okay. Okay. The first component has no delay. The second component has no delay, but the third component has an advancement by pi by 4 degrees. And what is omega value? Whatever is with t. For the first component is 100, next is 300, and the third component has third term has 500. Okay, so what is asked is a fundamental frequency in radians. So fundamental frequency in radians, to find out, you neglect the magnitude, you neglect any time delay, you see if they are all sinusoids. That's all that you need to do, and then you look at the omega component. Okay, because it is frequency in radians per second. So omega 100 into 3 is 300, 100 into 5 is 500. So 100 is going to be the basic value. So we have 100 as the frequency. Okay, in radians. Okay, as the period. Okay, on the other hand, if it's frequency that's asked, in the hertz, then you must remember that 100 is the same as equal to 2 pi f. So if 2 pi f is obtained, then of course division by 2 pi will give you the pi value. Okay, so I suppose this is clear. Okay, so even if 25 is given or 50 is given, please don't go for that, because here omega is asked. Okay, let's go to the next problem. Let fx be a real periodic function satisfying f minus x is equal to minus fx. Obviously, this is a minus fx, so it's an odd signal. Okay, so whatever is given is a odd signal or an odd function. The general form of its Fourier series representation would be, so if it's an odd signal, I hope we remember that it will have only sign components. It will not have either the DC value, that is A0, nor will it have AK. So from amongst the four options, immediately your eyes would go to the option B, where fx is explained as a Fourier series wherein you are having the entire summation for k going from 1 to infinity. Why does k go from 1 to infinity? Because a0 is not there. Okay, and b1, and we start off with b1, b3 by b1, b2, b3, etc. Okay, so bk sine kx. Okay. So k goes from 1 to infinity. Okay, I suppose this is clear. So let's move to the third problem. For a periodic square wave, which one of the following statements is true? We'll have to read all the statements because different statements are given. The Fourier series coefficients do not exist. This is ludicrous, because periodic square waves will whatever be the shape of the waveform, if it is periodic, you will have Fourier series coefficients. The Fourier series coefficients exist, but the reconstruction converges no point. This is not true. They do reconverge, but they don't reconverge at all points, because you have to go from k equal to 0 to infinity, or k n k or m, or minus infinity to plus infinity, depending upon the choice of the coefficients, the type. So option C, the Fourier series coefficients exist and the reconstruction converges most points. Okay, because we don't go up to infinity. Okay, the Fourier series coefficients exist and the reconstruction converges to every point. That's not possible, because it's a huge number of terms to be added together as the representation. Okay, let's go to the fourth problem. What is given is a square wave type of figure. It's not a pure square wave. It's a different type of square wave, but of course it is an even signal, because it is spread across over both sides of t equal to 0. Okay, ft is spread equally over both sides of t equal to 0. Okay, and the question is, of course, it's expressed because it's a Fourier series expansion of a of a component of this like this. And so what is asked is, okay, so from given below, contain the following non-zero terms. Okay, so what are the which are the terms that are going to be non-zero here? Okay, so we realize that it is it is an odd, it's an even signal, but that will not do because we have to go a little further. So let's see. So we have another way of handling this. Okay, why not consider this uh, as consider this as ft equal to 1 plus xt, where xt is an ordinary square signal, wherein the negative portions are now going to be cancelled out using the addition of 1. Okay, so when you add 1 to this, the entire signal, the negative parts get cancelled, so only the positive parts remain, and that will tell us what is ft. Okay, so if this is the case, okay, so now we can talk about xt. Okay, xt is now an even signal. It's also what may be called as a it is also what is called as a has a signal with a half-wave symmetry. If that is the case, then it has since it's even, it will have a0 and ak. But because it is having half-wave symmetry, a0 disappears, and at the same time the even values disappear, so only the odd values remain. But in this case, a0 is there because 1 remains. So 1 has also the fact that xt, since we have identified ft as equal to 1 plus xt, the a0 is now created, as also ak is created, but or an is created, where n is equal to n goes from n are all the odd terms. Okay, because even terms disappear for half-wave symmetry. Okay? This is another way of doing a problem like this. Okay, moving on to the fifth problem. The period of the signal xt is equal to 8 sine 0.8 pi t plus pi by 4. So what are the components that we need to unsee? One is of course 8, because for the period 8 does not matter. Similarly, pi by 4 does not matter. Now we have the period coming from 0.8 pi, because that is going to give us omega as the coefficient of t. So 0.8 pi is omega, which is equal to 2 pi f. So you can find out f from it as equal to 0.4. And so what is t? The period 1 by f, which is the same as equal to 2.4 seconds. Okay, as simple as that. Okay, so this is a simple problem in this. Okay, in this session. Moving on to the sixth problem. What do we see here? A sine kind of wave. Of course, it's a square waveform. So it has both. It has odd symmetry, because if you fold it and then refold it again, both along the magnitude as also the time axis, you get the same signal. Okay, so we have what is called as a odd symmetry. It also has half-wave symmetry, because if you shift it by half the period, which means that what was originally negative becomes negative here. Okay, negative in the t equal to 0 plus axis, and then what was positive there, it shifts by half a period. Okay, and then you fold it again, okay, or invert it as is the explanation for half-wave symmetry, then you get the same waveform. This is what you have, what you mean by odd plus half-wave symmetry. Okay, so obviously so much is known to us. Let's read the problem. The second harmonic component of the periodic waveform given in the figure has an amplitude of. So what do you mean by second harmonic? The even signal, the even part, the one of the even coefficients. So the even coefficients don't exist. Why? Because it has half-wave symmetry. So it's equal to 0. Okay, coefficient is equal to 0. Very simple. Okay. Moving on to the seventh problem. Here, xt is a real valued function of a real variable with period t. Its trigonometric Fourier series expansion contains no terms of frequency. Omega is equal to 2 pi by t, which is omega naught, into 2k. Please realize 2k tells us that k is equal to 1, it's 2, and k equal to 2, it's 4. It's always going to be even. So it has no even terms. So immediately we realize that it has half-wave symmetry. Also, no sine terms are present. If no sine terms are present, it has what is called as even symmetry. So even half-wave symmetry is there. Okay. So now it's very simple. You can see that then xt satisfies the following equation. For one thing, it's periodic. Okay. Otherwise, it won't have a Fourier series expansion. So x t minus t, xt is equal to x t minus t. with the minus sign taken out, which means that it's no, that's not true. Okay, that's not true because it is even symmetry here. Okay, it should have been xt is equal to xt minus t for even symmetry. Okay, so that's excluded. That is, a is excluded. B is okay. Xt is equal to xt minus t equal to a minus of x minus t, which is again wrong because it is violating the understanding of even symmetry. Okay, so option C, xt is equal to x t minus t. That's right. Capital T minus t means you can take out minus, but still it does not become negative, which means that it has even symmetry. Okay, minus of x t minus 2. This is exactly what you mean by shifting the signal by half its period and then inverting it to get the same xt. Okay, so that's the second second equality that is given there, equal to minus of x t minus capital T by 2. Okay, so that's the right one. So if you compare it with D, wherein the first quantity is okay, but yeah, so the yeah the yeah the which is not true. Okay, we have that yeah, we of course the second answer is okay, but the first one is not. That is, xt is equal to xt minus t is not right. Okay, so let's go for yeah, let's go for the eighth problem. Okay, eighth problem, periodic rectangular signal xt has the waveform shown below. Frequency of the fifth harmonic of its spectrum. That's all that's asked. So we can find out the period and we can find out the fundamental frequency, then multiply it by 5. Okay, so how do you find the period? You start from any point. Let's say at t equal to 0, you start the signal, and then it goes up. Okay, and then it goes down at 2, and then it goes negative, and then at 4 it repeats. Okay, it starts to repeat the same kind of periodic kind of recurrence that is existing, that is inherent in xt. Okay, so we see that now the period is equal to 4. Okay, and that's in milliseconds. So if you want to get the frequency, you have to take the reciprocal of it, which is equal to 250 hertz, then multiply it by 5 to get the fifth harmonic. That's equal to 1250 hertz, or the fourth option, or D option. Okay, let's move to the last slide, the last problem. Only here we are finding the coefficients. We are just guessing in most cases, or trying to use our intuitive understanding. Okay, the ninth problem, a periodic function ft with a period of 2 pi is represented as its Fourier series. Ft is equal to a0 plus n equal to, okay, as usual, this is the normal representation of a Fourier series expansion for a periodic function ft. Okay, so there are three components. One is the DC value a0. Okay, sometimes it's written as a0 by 2, sometimes simply a0. Okay, and then from n equal to 1 to infinity, there are two components, two terms, two series of terms which are added together. One is an cos n t, the other is an sin n t. Okay, and ft okay, now the description of the signal comes, or the waveform comes as ft is equal to a sin t, which is a sinusoid, which but of course the sinusoid exists only between 0 to pi. Okay, thereafter it becomes 0. Okay, and then the whole thing repeats after 2 pi. Okay, yeah, so it's a periodic waveform. Okay, so it's on the other side of t equal to 0 as well. Okay, so it's just an indicative waveform has been drawn there. Okay, yeah, so now what we need to find out is the Fourier coefficients a1 and b1. Okay, obviously it's a yeah, so you okay, let's proceed further. That may be better. Yeah, so in a1 we have, just for this case, we are finding the Fourier coefficient as 1 by pi is the period. Okay, take the integral from 0 to pi of a sin t, which is what is existing between 0 and pi. Thereafter it's 0. That's why we take only from 0 to pi. Otherwise, you could have taken from 0 to 2 pi, the entire period. Okay, 0 to pi a sin t multiplied by, to get a1, multiplied by cos t, cos 1 t. Otherwise, it would be, for a2, it will be cos 2 t. Okay, so we are asked only a1 and b1. So cos t dt. Okay, so now sin t cos t will give you sin 2t by 2. Okay, and sin 2t, if you integrate between 0 to 2 pi, you will get 0 only. So a1 is equal to 0. Okay, very simply. Okay, so whenever you are having a sin value integrated between 0 to pi, or 0 to 2 pi, you are going to get 0. Okay, so remember that. Okay, sin 2 theta, sin theta, everything is that. Okay, on the other hand, b1, because we are getting 1 by pi, integral 0 to pi as same as before, and then a sin t multiplied by sin t again. Okay, because sine 1t. Okay, so in the subsequent components it will be sine 2t, etc. Okay, so sine, because we are asked d1 only, so it's sine t multiplied by sine t. So sine square t. Now sine square t has a good way of representation where we are having 1 minus cos 2t by 2. Okay, so 2 is taken out, a is taken out, pi is taken out, and we have 1 minus cos 2t integrate. Okay, when you integrate cos 2t between 0 to pi, it becomes 1 minus 1, so that's gone. But 1, when you integrate, you get a value equal to pi t, and then t, we're taking the two limits, pi and 0 becomes equal to pi. So altogether it's going to be a by 2. So this is the final version. I hope I'm making it short because I'm not because I think I can recapitulate in the final slide. That may be easier. So some difficulty with my voice. Thank you.